Okay, so this lecture is going to be about the two different ways of solving physics problems. One way is to iterate. That means that we need to update the momentum, for example, the velocity, the position, by understanding what happened in the past to predict or to enable us to calculate what's happening now and into the future. That's using discrete time steps. We say some time delta t has elapsed. We utilize that to calculate the impulse. We plug that into an addition with the current value of the momentum, and then that results in the momentum at a later time. And we can do that as long as we keep certain things small, like delta t, or we have things like forces that are constant, for example. And we're going to see the differences between that now, where how we can calculate things like average velocity accurately, what's the best way to do that. We're also going to talk about analytical solutions, which are solutions that depend on time, but in a continuous way. So we don't have to do this iteration process. We have an equation that tells us for all time what the solution will be to our position or our momentum. And that means we'll have functions, actual functions, that we can plug time into and get an exact solution for what those values should be. Okay, but that means we have to understand something about the dynamics, how things move in time. And so we've seen in a problem that we solved in class that, for example, the average value of the velocity can be calculated by assuming an approximation. And that is that the approximation is that the p future over m is actually the average velocity. And this is a good approximation if, and only if, the time interval is small and the force is constant. And so that's an important aspect as to why we would use such a thing. Why didn't we calculate the average velocity, or why wouldn't we just calculate the average velocity by doing our classic way, delta r over delta t, which would be r final minus r initial over t final minus t initial. The reason for that is because in the case of kicking a ball, we don't know where the positions will be. We don't have knowledge about the trajectory of this ball. The trajectory is something we want to understand. And so we can't just plug this directly in and say, I know the average velocity at all points in time because I know where the ball is going to be at some time later. I want to perhaps calculate this value of delta r, or of r. And so we can't necessarily do this. Now there's another way to calculate the average velocity, and that is what's called the arithmetic average. So the arithmetic average is the mean, essentially. That's what I'm saying, is the arithmetic average to calculate the average velocity. So we'll take v final minus, v final plus v initial divided by 2. That's just the average. So these are all methods that work. I'll take away this. If we know something about the position, we can calculate the average velocity, or the change in position we can calculate. If we know something that is well behaved, that is that if the delta t is quite small, the force is constant, we can use this very simple definition of the average velocity. Another way to do it is to take the average of the two velocities given in 2 units of time. So these two values, final plus initial, divided by 2 just gives you the mean. And so I have over here two cases. The first case, and I'm going to explain what this graph means. The first case, this is the value of the x component of the velocity over time. So what is the velocity doing? It's increasing in time. So you could say that this thing, whatever I'm measuring, is accelerating. The velocity here is different than the velocity here. However, this line is nice and straight. It's well behaved. The reason that it's accelerating in a linear way is because the force is constant. The force is constant, and so therefore this thing is just growing in time. So if I take these 2 points, here and here, and I plug them into my equation for the arithmetic mean, I get the value right in between, because it's a simple analytical way to solve for the average velocity. So if this was 6 meters per second and this was 8 meters per second, well, the average velocity, of course, would be 7 meters per second. 6 plus 8 over 2, 7. Now, I could also, for example, if I shortened the amount of delta t to very, very small interval, to a tiny interval, if I took delta t to be very, very small, somewhere in here, then this approximation for the average velocity would also be consistent. That is, if I have a very, very, very small interval, the average is basically not too far away from the value that I have at my final or even my initial. I could plug in the initial value here. I wouldn't be too wrong. So always in physics we have to sort of weigh the benefits against the negatives. And the benefit here is that I have a very simple way, if and only if I choose my delta t quite small. Let's go to case 2. Case 2 is quite different. Look at the velocity curve on case 2. It starts out over here, it's slightly high, and it goes down in time, so it decelerates, its speed is going down. It hits some flat value, it's not accelerating here, and now it speeds back up. So for example, this might be a car on a racetrack going around a turn. It's got a high speed, it gets close to the turn, it decreases its speed by hitting the brakes, it goes around the curve. This isn't position now, this is velocity. So I'm mapping out the velocity of a car that then hits the straightaway and wants to accelerate, and it tries to go as fast as it possibly can. But if I asked, well, what's the arithmetic mean velocity in the interval t initial to t final, well, I would get an answer that doesn't really look like the actual value of the mean velocity. This velocity here is way too high. If I just take this time point and this time point and plug them in here, I get a value that's extremely high. That's not representative of the actual average velocity over this time interval. I could calculate it directly using this, but I would have to know everything about every step along the way, and it's somewhat complex. So I have to come up with ways of solving this sort of problem, of figuring out what the average velocity is, and sometimes it just comes down to shortening delta t. So that's an approach that we're going to go through. All of these are correct. None of them are incorrect. It's just where you apply them gives you values for what's called accuracy of your prediction or of your calculation. So they're all valid ways. You just have to choose the appropriate one for the problem that you're working on. So this would be small delta t. This would be if you knew something about r, if I have r information. This would be if my force is constant. If my force is constant, I could probably use this without a problem. Okay,